Hi everybody, I'm Carlo, that's Jonas and that's Arne, and today we are here to speak about the functional programming paradigm in the example of ReasonML. So, I don't know, if your education was anything like mine, you don't have the nicest memories of functional programming. So I still vividly remember my course in university, where some esoteric guy tried to convince me that there was another functional programming paradigm called functional programming and that it was great and you could actually use it to build software, which you could also build with the other paradigm. So I didn't really get what it was about. Honestly, I hated every second of that course. I don't know whether I was a good student there, and still, yeah, so I left that course. I was under the impression that functional programming was something which nobody was using in reality and which had little to no application cases in the real world. And there's actually data to back this up. So if we look at the Stack Overflow developer survey from this year, we can have a look at the question where people have been asked what technologies they have been using in the last year and they want to use in the next year. And then we'll see an interesting list of programming languages and technologies, and we actually have to do quite some scrolling until we hit the point where we find the first language which is highly associated with the functional programming paradigm, and that would be Scala here down with 2.6%. And if you scroll down further, you'll suddenly find more functional programming languages. And still here we are speaking about functional programming languages or the functional programming paradigm. And to put a dent into this picture I had, at least after my introduction course to functional programming, we can look at other data from the very same Stack Overflow survey. So it's definitely not used by a lot of people, so that's true. But this other aspect, it's not usable, right? So if we look at other questions in the very same survey, so there's a question about compensation. So how much money are people making if they know specific technologies? And this is the interesting picture. So in the very top we see functional programming languages, and quite a lot of them. Clojure is the language the guy who spoke here right before us was speaking about. So if these languages wouldn't have any real-world application cases, why would developers knowing these languages suddenly make money? It doesn't make a lot of sense to me. So that was the first thing which put a dent into this thing. So I've been using these languages quite a lot recently. And I've attended conferences, I've seen people speaking about them, I've seen people at a lot of major players using these languages in productive scenarios. And well, we three are from SAP, so some of you might consider us to be also a larger company. And we are using a functional programming language to build a product which is live and running. It's a cloud service called the SAP Master Data Integration Service. It looks very, very simple in this example. So essentially it's something which synchronizes data between independent applications in an SAP ecosystem. So these can be SAP applications or third-party applications. It doesn't matter too much what it's doing. It looks very simple. So in this example, there's a cost center being created. It could be a workforce person. Doesn't matter. So there was an interaction in one of the systems which caused a change to the data. It's communicated to the service. It's communicated to the other participants. I know it sounds ridiculously simple, not silly, but the challenges lie here in scale and things like concurrent updates, GDPR compliant filtering. If you have to incorporate all of that, even this task becomes interesting, especially if you look at a company like SAP where customers come with 15 terabytes of this data and then you have to cater to the full SAP installed base, which is significant. Okay, so when building this service, we were looking for people a while back, especially so if you think about what we kind of needed, we need people who were familiar with data storage technologies, and these are not easy to find. So we were looking for new people to join our team, and when doing so, we found Jonas, and we stumbled across his profile. He recently finished his PhD in database systems, and unfortunately, he was for some reason not familiar with the language we've been using, because we use ReasonML. I guess almost none of you, if at all, know this language, except for those guys who saw this other talk on this very niche language yesterday. So we interviewed Jonas. We liked his database skills. We had a look at his CV. He had all his fancy Java certifications. We tested his Java knowledge. It was on par. And then we asked him whether he wanted to join and learn ReasonML with us. And today we are here to speak about Jonas' experiences as somebody who is coming from the traditional Java world, joining a team which is using functional programming languages. And we're going to take you along on this journey. So you will actually be able to take out your laptops and do some of the things yourselves in the later part of this talk. So without any further ado, the stage is yours.
Okay, so let me take you on that journey, as Carlo said. We will do that here as kind of a hands-on hackathon. On the first part of that hackathon, I will actually walk through some things which came to my attention or which appeared important to me when I started coding Reason, or when I started coding more in functional programming when compared to what I actually did before. And then in the latter parts of this hackathon, this is actually a double slot here, we go to more and more parts where you can have actually more and more hands-on experience. So let's start with something simple. The first thing I asked when I wanted to start coding Reason is, how do I actually declare a variable? And the answer I got from the team, you don't. Okay, so why do we not declare a variable? The key point here is that in functional programming, there's this design choice to have immutable data wherever possible. And this actually also exists in Java, right? There's this final keyword, or in JavaScript, there's this const keyword to define basically constants. But especially in Java, it's not so widely used. However, if you check for Java tutorials on immutable objects, there are a lot of people advocating using them. And just to give you some examples, they say that it gives you a better readability of the code, a better maintainability of the code. It gives you easier refactoring. It helps you with thread safety. So a lot of advantages actually, which are pointed out from using those immutable data points. Still, when I started, not being able to do something like start time is start time +1 was actually quite hard, and it requires you as a Java developer or someone who is familiar with imperative programming languages to rethink a bit the way you code. But let's look in what we do in Reason instead. We have something called let bindings. And Arne will just type some very basic declarations here. So we have what's called let bindings, and so we can have a conference here, which is just the string code.talks. We can have a conference with a year, so there you can also see how one would append something to a string with a ++ operator. You can basically add the year to it. And we will see some other literals as well, like integers or float values. So far, so simple. One other thing to notice here is that there is little to no operator overloading. So from the operator, this ++ or the plus when you add some integers, or here for the floating point operations, the +. You know from the operation exactly what data types this operation deals with, which is different compared to what I was used to from Java, for example. Another thing what you noticed here is, where are we? Another thing what you probably noticed here is that Arne did not declare any types. So there is another very important feature, which is maybe a bit more particular to ReasonML, which is that there is a very strong type inference system. So what is this type inference people keep talking about when they talk about Reason? You see here on the bottom an example, which is that the compiler infers the types. Okay, for these constants we see here, that's quite easy, right? Because the literal on the right side of the assignments tells the compiler what type of data that actually is. However, when you have very complex functions, function calls over several levels, and quite complex data structures, then this type inference becomes an extremely powerful tool. And one thing what really surprised me when I was starting in the team is how fearless we were refactoring the code. So even in the very beginning, like the first weeks I was in the team, we did some introduction calls where Carlo and Arne introduced me to our code base. whenever we noticed that something was hard to follow, hard to understand, we would just, within that immediate call, fearlessly refactor the code and file a PR as a side product of our tutorial session. And just because we have this type inference system and some other means Reason provides us, we can be quite sure that if we would break something, it would actually come to our attention. Because the compiler would notice those type mismatches, it would notice missing cases, and so on and so forth. Okay, so to give you some more example, let's actually go a step further and implement something. So what we are going to implement is just a binary tree structure. So maybe just to give you like just to give you a feeling on how that actually works. It's inspired from the tree set you would have in Java, but we are just doing a regular binary tree, not the red flag balanced tree version you would regularly use when you just use the Java default. Okay, so what Arne will type is basically the basic declaration of our tree. So we declare a type here, the type tree, and the type tree has actually two options. It can either be an empty tree or it can be a node which has some value and then subnodes on the left-hand side and the right-hand side. What you see also here is what's comparable to the Java generics, so that tick A Arne used here. This is actually a placeholder for some arbitrary type, so we can use that tree declaration later on and put strings or integers or whatever type we want to put to store in that tree. Okay, so let's implement some basic functions to use in that tree, and as first I would like to go ahead and implement some contains function. And this contains function also brings us to another very strong feature of the language, which is the pattern matching. Can you switch the slide?
Sure.
Oh. No, sorry, I missed one part. So we first initialized this example tree. As I said, it's a binary tree, and because we didn't implement a nice add function, we prepared that snippet of the code to initialize the tree. So this is actually what our tree looks like with the example data, and now we are going to implement the contains function. Okay, so within this contains function, we will use the powerful pattern matching feature. It's something which I consider extremely safe, intuitive, powerful, efficient, and readable, and which is extremely widely used in our code base. A very important point here is that the compiler will always tell you what is missing. So if you implement now this contains function, and maybe we can first have a look on how that contains function actually works. So in this contains, we have a mapping here where we have the tree T and the value, and we map that to this pattern matching part, which is the switch. So in the in the first case of that switch, we actually look into what happens if the tree is empty. So if the tree is empty, we can just return the Boolean value false. And then we look into what happens if the tree contains a node. So if the tree contains a node which has the value v tick, and then we can have a when condition where we basically compare this value v tick to the value v we got as a parameter to the function. This is basically exactly the same as the Java comparable you may be used to. So if that is equals 0, then we map that to true because we found our search value. And then we have other cases where we look into navigating in our tree, so either navigating to the smaller values on the left-hand side of the tree or to the larger values on the right-hand side of the tree. So this is again this compare function where we have the v and the v tick, and depending on whether that is smaller 0 or larger 0, we have a recursive call to that contains function, which then searches for our search value in the left subtree or the right-hand subtree. Okay, great. So maybe we can have just a check and compile that and see what is the output, because this brings us to a typical warning or error message we often see. So here the compiler says us that we might have forgotten to handle a possible case here. So for example, the case where the node is any of the values. Okay, that's a bit weird. So what happened here, if we go back to the code actually, we have used those when conditions. And these when conditions basically mean that the compiler doesn't know whether or not we have addressed all the possible cases within that switch statement. So it could theoretically be that this compare function has some side effects or so, and it's not necessarily going into any of the cases. So how can we resolve that? As we know that it does not have any side effects and that we want to navigate to the right-hand side of the tree if we are in the last case, we can basically just remove that when condition from the last case, and then the compiler can be sure that we have addressed all the cases in that switch statement. And of course here this is more or less simple. We have just 3 cases. But if you are in a very complex software system where you have a huge number of cases and you have complex different combinations, and then you want to do some refactoring, going back to that point of fearless refactoring I mentioned before, it's really powerful that the compiler can check for you whether or not you have handled all the cases, and it can also ensure or enforce that all the possible cases are actually handled. Okay, so let's look into one more important thing. So who of you is a Java developer actually? Who's used to develop Java? Okay, great. One thing every Java developer has to deal with is null pointer exceptions. So let's look into how we would code such a tree in Java. We would basically have some class node. It would have an integer value in this example here. And then we have a node on the left-hand side and a node on the right-hand side. And in the constructor, we would initialize that with some value, and the right-hand side and the left-hand side would just be null. So whenever we now use this node class and we navigate in the tree, we have to ensure on the call side that we handle those null cases. Otherwise, we potentially get this null pointer exceptions. Of course, there are ways around that and ways to secure that. But in Reason, we have a very nice built-in way of doing that. So there's nothing like null in Reason, and in the entire time I've been into the project, I've nothing seen similar to a null pointer exception. So let's implement the max function, which searches the maximum value in the tree. And how we actually will do that, let's again look at the signature Arne will type here. We have this recursive function, so let rec always means that we do recursive calls where we map the tree, again with some pattern matching to result value. So if the tree is empty, we can return a value which is called none. And if we have something in the tree, then we return a value which is called sum of the max value we found, right? So if to find the maximum value, we have to navigate basically to the rightmost node in the tree. So if we have the right-hand subtree empty, then we know that we have found the maximum value, return some value which we found. And otherwise, we do a recursive call of that max function to navigate to the right-hand side of the tree. So the amazing part here now is that the compiler ensures on the call side, now remember like handling all those cases above there, right? If I use this maximum value in some switch statement or some call statement, the compiler will ensure for me that I have handled the none and the sum case. So that's also a feature I consider very strong, and which makes it much more maintainable and much easier also for people like me who even were not so familiar with the programming language to actually get started. Okay, there's one more point which I want to highlight because it's an important part of my experience starting to code in ReasonML, not in particular in functional programming, but particularly in ReasonML. But that has nothing to do with what I can show you here in code. So maybe can you switch to the next slide? So it's the difference in the communities. So there is a reason for being lonely. And that actually means if you are coding in Java, you can basically Google any problem and you will find at least 100 people who had the same problem before you. That's at least for all the beginner questions that holds true. There is a much, much smaller community around the Reason programming language, and you need somebody who can actually help you to get started. Either you start by some books, you start by some tutorials, or you start with very nice team members who can help you. But when you think about starting a Reason project, you maybe should also think about who is there to support me doing that, who can help me, which problems that might appear, because sometimes it's really hard to find solutions for questions, as it's not so easy actually to Google that, and not everything is on Stack Overflow. Okay, with that little disclaimer, now that we are here to help you guys, we would like to start code something where you can have some hands-on experience. And given the example now we have here on the left-hand side of the slide, what we would like to ask you is to implement a linked list, basically using the same structures which we just showed you. There is a very nice environment where you can just do that in the browser and also see what is the results. So either you type in your computer tinyurl /learn ReasonML, or you scan the QR code, then you also get the same URL. And I think that we will walk around a bit, help you if you have questions. And then after a few minutes, we will continue showing how we would implement this linked list. And from that, we will proceed and show you more and more features of the Reason language.
Okay, yeah, then I will just start to type down the three. So basically, right, the linked list, yeah. Basically, linked list has two variants, right? So as a usual list or an array, right, it can just be empty, just like the tree we wrote down previously. So the first thing we can do to define our linked list is to say, okay, our linked list can be empty, right? There's an empty variant. And since this is, it is linked, right, some linked list object or linked list variant always has one element and the link to the next link object, right? So let's just add another variant, just as we did with the tree above, which we call node, right? And then we add an element and the link to another list. Good point. Exactly, yeah, and that's basically, okay, I have some compiler. Let's look into it. Ah, all right. I already used the type T, so I can't declare it again. Let's call this list. And we, of course, also have to rename this to list. Okay. So now let's also maybe add some function to the list, right? The list itself is not very useful yet. I mean, we can use the constructors we've already wrote down, right? We can just say, okay, I have a list called L, and this is maybe empty. Or we can redeclare it and say, okay, the list has one member, and empty, right? Things like that. That already works. But there's not much use in it yet. So let's add a function that can prepend things to the list, right? So we get some list and an element we want to prepend, and let's just try that. I will give you guys some time if you want to take along, yeah, until I will start writing down what should happen. Okay, so I would like to continue with the prepend for now. So prepending on a linked list is fairly easy, right? Since the linked list, if you want to add a new element in the front, you just create a new node, right? You say node, you give the value which you want to prepend as the first thing, and then you just link the old list, right? And since everything is immutable, this will create a new list. So the prepend is a fairly easy case. So let's get to a more challenging example maybe, and let's try to implement a contains function, right? To check whether some element is in the list. And what I can already tell you as a tip is that this function would have to be recursive, right? And it gets a list and a value, and then you can check whether it is contained. Okay, I would maybe just start a little bit, and yeah. So the contains of the list is pretty similar to the contains we did for the tree before, right? So we will also leverage the switch statement again to check what kind of list we are dealing with, right? This time we have two variants. The first variant is the empty case. And if the list is empty, it doesn't contain any values, so we can directly return false. And if it is a list with some values, we have the first value we can compare now, and then we have the tail of the list, which can maybe contain other values as well. So what we want to do here is we want to say if value, if the return value of compare for the value and the value of the tree node is 0, they equal, right? And then we can just say that the tree contained the element. And if that's not the case, we of course have to check whether the other trees, right, the tail of the tree contains the element. So we just call contains again on the tail as a recursive function call. Okay, so now we actually have another case which is quite interesting, especially for linked list, that we want you to maybe check out or to try out, which is append, right? Appending something to the end of the list. Okay, so if you want, just try with the same as with the prepend case, but now instead of appending it on the front, right? Prepending it, we want to append it. So I will give you guys again some time to do it yourself, and I don't know, in a couple of minutes I will start implementing it myself. Okay, so I will just start implementing the append case. Again, since it's very powerful and very useful in Reason, we'll just start with a switch and check what constructor of the list we are dealing with. Let's start with the easiest case, the empty again. Now we have to think, right? If the list is empty, we should.
Sorry if I have to interrupt you, but
okay.
In the contains function, you wrote tails plural. I don't know if it's intended or it's just a typo.
It's a typo. You're right, and the compiler would probably complain. Let's check it out. And yes, there are some compiler errors. Let's check. The value tails can't be found. Yeah, exactly. Thanks. Okay. Unused value contains. We called it different. Let's say list contains. All right. Thanks. Okay. Let's do the append. So we have this function append. We get a list. We get a value. Then we do our pattern matching on the list again to see what type of list we are dealing with. Let's start with the easiest case again, the empty case. If the list is empty, appending is just like prepending, right? We just create a list with a single element, which is the value, and at the end of the list, we have again the empty list. Now it gets trickier, right? Did I call it cons? No, I call it node. If we have the node case and we have another element, we know that we can't. So we know that we have to traverse until the end of the list. So we actually have to call append on the tail again and create the list, right? We have to keep the list the same. We have to still keep the value in front, and then we basically have to append the value to the tail, right? So what we are trying to achieve here is we want to traverse to the whole list and put and append the element on the last list, right? So we traverse to the whole list until we get into this case, our base condition, right? Until we have reached the empty list constructor. And if we have reached the empty list constructor, we want to construct a new node at the end of the list, assign it the value, and then append the actual end of the list again. And while we're doing that, right, while we're traversing to the list, we want to keep the list the same. That's why we redeclare this node here again, and then mutate or work on the tail of the list. We don't actually modify some existing value because we are dealing with immutable values here. We basically create a new tail.
Okay, great. So I'm here again to talk about Java one more time, because I think that is a good point to again compare what we have now seen in the functional programming part with Reason to what is happening in Java if you have a linked list. So the Java linked list type basically has also this generic type. It's called E in the Java framework, and it contains a node of type E, which is the first node of the list, and a node E, which is the last node of the list. And the Java linked list has the speciality that this per default is a doubled linked list. So here on the top you can basically see visualized how the linked list, doubled linked list in Java would look like. And since we have mutable data structures in Java, we can easily have add last method, and that would have O1 complexity, right? Because as you can see here with the red arrows, the only thing what we have to do is we create that new blue node here in the very end, and we change the 2 pointers, the red ones, and we have with basically only one step added a new node to that list. So compared to what we have seen here on the what we have seen here in the append function Arne coded, that's way less complex, and that's indeed a disadvantage you have when you implement that with immutable data structures. That if you want to append something to a list, it basically means that you always have to do that with ON complexity. However, that problem is not as complex or as problematic as you might think. So let's look at another function. There's also, for example, the remove last function. Also here, what you would do in Java is you would just change the 2 pointers such that you have now the pointer pointing to the last element, you change it to point to null, then you change the last pointer of the list wrapper pointing to the new last element, and the item we want to drop from the list would just be removed by the garbage collection of Java. So now let's go one step further maybe. Let's revisit the advantages again of immutability and think about why we still may want to have immutable objects, and I just copied here from some Java tutorials. So since the internal state of an immutable object remains constant in time, we can share it safely among multiple threads. So as you probably know, the Java collections, they are not thread safe. If you want to use them in multiple threads, you have to either have proper locking on the functions with some synchronized object or some object you synchronize on, or you have to put a synchronized wrapper which drastically reduces your performance. We can also use it freely, and none of the objects referring it will notice any difference. We can say that immutable objects are side effect free. It's another advantage which we can point out, and from yet another tutorial they say it makes it easier to have to create dependable applications, and code can be easier, more precise and less blunder than with mutable objects. Okay, so let's look into something like a FIFO queue, something where we regularly want to remove the last element of the list, and think about how we could actually have a workaround in functional programming which is highly efficient and still works with the functional programming paradigm. So I want to walk you through an example for a first in, first out queue in functional programming with immutable data structures. So that example, of course, would also work in Java. So if you for some reason or at some point want to have an immutable FIFO queue in Java, that could also be your way to implement that in Java. So can we switch to the next? Okay, so let's go for the immutable first in, first out queue. What we start with is just the empty queue. Then we want to add our first element. So here, this is going to be just the item 1. So if we add the item 1, we just prepend it to the list. Okay, let's add some other values. So we add a value 8 and a value 43. We again can just prepend it to the list. Now one more step. Now we want to pop an item. And of course now we have to play some trick. So since we cannot just remove the item we added first, the one from the list, because these pointers, so the pointer from the 8 to the 1 is immutable, we need to find a trick. And the trick is that we can do that using two lists. So what we do is we basically invert the list we have here on the top into a second list, and then on the inverted list we can actually remove the first element, which then is no problem with the immutable data because we don't need to change the pointer included in this node 1. So now if we continue with that example, in the next step we add two other items. So we add the value 15 and the value 16, and here you can already see a pattern. So whenever we add a value now, we add it to the top list. Whenever we pop a value, we remove it from the bottom list. So let's continue and pop two more values. Here we pop the values 8 and 34, and we can just do that by removing them from the bottom list. And now if we continue even further and pop more, we are again at the stage where we reverse the top list to the bottom list and pop the last value from the bottom list. So just to summarize how that would actually work, that FIFO queue with immutable data, whenever we insert, we prepend to the top list. Whenever we pop and the bottom list is empty, we revert the top list into the bottom list. And whenever we then pop a value, we pop it from the bottom list. So these are basically the three operations we do. And our next step will be to implement this FIFO queue in our Reason code. So we keep you these examples here on the slide so that you can always basically check what the syntax will be, and Arne will continue actually coding that on the Reason side. Maybe you can give us a brief feedback if you would prefer us to just continue coding that here, or if you would prefer to have some time to test it yourself. Who would like to test it first? How far you get yourself? Okay, who would like us to just continue Arne showing what we are doing? Okay, that's majority. Then Arne, the stage is yours again.
All right, then let's do this. Okay, so basically, like Jonas already explained, right, nicely, with our immutable queue case, we have two different types of two different lists. One is the head list, where we insert elements, and the other one is the bottom list, where we remove elements. right? So basically what I'm doing here, I'm declaring a tuple, right? I'm declaring a tuple that contains two different types of list. So a tuple is just some fixed length vector, you can imagine it like this, right? You can't remove any elements from it. You have a fixed number of elements, and the type of the vector is statically fixed. So you can have different types within the tuple. It's a pretty nice feature, but it's also not that interesting. Okay. So we have two types of lists. One is the head list, one is the bottom list. In the head list, we prepend the elements when we insert, when we push. And in the bottom list, we want to pop. So that when we push and we pop, we always have constant time operations in for most of the cases. So let's start to implement this, and let's do the push first. So in the push case, we get a queue and an element, and we basically want to return the new queue with the element appended to the queue. So what we are doing is, first thing we have to do is we have to execute the switch again to basically get the pattern of the tuple, right? We want to access both values, the top list and the bottom list. And since the push case is very easy, we just we prepend the element to the top list. It's only one case we have to look at, and we just prepend the element and return the bottom list as it is, right? We don't even have to touch the bottom list in this example. So since the prepend operation of the list, that's the wrong list, right? Since the prepend of the operation of the list is constant time, right? We basically only have to one step. The push operation is very fast. Let's get to the more tricky example, which is the pop operation. So in the pop operation, we basically have two cases which we have to handle. The first case is the fairly easy one, when the bottom list actually contains elements we can pop. So let's do the pattern matching. Top list, it doesn't interest us. We just assign it a name so we can access it later. And for the bottom list, we have to do some pattern matching. It doesn't actually get an element. We do some pattern matching and say if it is a node, so if the list contains some elements, we want to push the first element. And if that's the case, we just return again a tuple of the element itself and the new queue where we remove the element.
Syntax. You need to explain.
Oh, yeah. Forgot that. Thanks. Exactly. And then we also have the second case where the bottom list actually doesn't contain any elements. And in that case, like Jonas already explained, we have to reverse the top list, right? Because the top list contains the elements that are inserted in the basically different order, right? The element which was inserted last is at the end of the list, and if we wanted to remove it, we would have to traverse through all list elements until we get to the element we actually want to remove. And we would have to do this in all pop operations, which is not feasible, or not, I mean, maybe not the thing that we want to do. So since we do not have any function which we can use to reverse the list yet, let's write our own one. List reverse. And now, when reversing the list, we actually have we can make use of a trick. We have to, since we cannot simply, reversing list is very difficult by just providing the list in the recursive list. So we just make use of some intermediate state variable where we basically reverse the list, right? So every element we remove from the top, we put on this intermediate state, and all the other elements we remove, we just prepend it to the list until the list completely reversed. Let's see how that looks like. We call this intermediate and switch on the list. Okay, let's handle the empty case first. If the list is empty, right, we just return our intermediate state. And if the list has a node and some tail, what we now do is we call list reverse again on the tail, and then we prepend the element we just saw in the node to the intermediate state we already have. So what it does is, if you think about it, right, if you start at the top of the list and take the first element, if you start at the top of the list and take the first element and prepend it to the intermediate state, it actually becomes the last element, right? Because as soon as you get to the second element, it's prepended to the first element, and the third is prepended to the second element, and so you can reverse the list just by traversing through it once. And since this list reverse now has 2 arguments, or even though it actually only needs 1, we can just shadow it, right, by declaring it again. So by shadowing means you declare the same variable again, which makes the other one not accessible for the rest of the script anymore after you have declared the second variable. And for the shadowing, we just have 1 parameter and then provide the first value for the intermediate state variable for the list reverse function. Okay, now we have some compile errors. Let's check them out. That's probably because we haven't implemented this case yet. Yes, we forgot to handle the case here. Okay, let's do that. Now that we know how to reverse a list, let's do just that. And say, okay, we want to pop an element from the queue that has an empty top list and the reversed top list as the bottom list. Right. This is just the example Jonas showed in this case. If we notice that the list is empty, in this case here, right? If we notice that the bottom list is empty and we cannot simply pop an element from it and access it in constant time, we reverse the top list and put it as the bottom list, which makes the top list empty, and then just take the first element from the newly created bottom list. Yes. Yeah, that's just muscle memory, I guess. Yeah, so basically what this pipe operator does is it takes the thing, so this arrow operator, it takes the thing before the arrow and puts it as the first element of the operation, of the function here. So basically the same thing, I could just write it down this way, and it is probably easier to understand for you. Okay, now that we've implemented the pop operation, let's see whether it actually works. Let's declare a variable called queue, which is empty at first. And then let's push some elements. And then let's see what happens if we pop a value from the queue. Okay, what we can do now is we can execute the script here that we just wrote and see it isn't actually that nice. Let me make it a little bit nicer. right? So the pop function returns the element we just popped and the new queue. And we can just log the element here to get a single value out of it. And we see, okay, the element which is inserted first is also returned first. Nice. Okay. Let's get to another important aspect of functional programming, which is recursion, and look into it in more detail. One of you already mentioned it, whether the ReScript compiler supports tail call optimization, and that's basically what we want to look at now. So, but before we actually come to tail call optimization, let's first do another recursive example again. And in order to do that, we will just write down a function called sum, which can sum up a list of integers to the end value, right, to get the sum of it. So we take a list. It's pretty easy, just like the other functions. We just do a switch again. Obviously, if the list is empty, the sum of all the elements is 0. And if the list has an element, we basically have to sum the element up with the one element up with the sum of the tail, right? So basically what we are trying to do here is, since we only can sum up 2 integers at once, and we can only look at one value of the list at once, right? We basically say we always want to sum up the head with the sum of the tail. So basically we are going through it recursively and build up our sum as we go. Okay. In order to understand this recursive function a little bit better, let's look at how this is actually executed. What happens if we would execute this function? And most of you, or some of you, might already know, on a very primitive level, when you execute your function, it makes use of a last in first out call stack, which stores the execution context of your function, and a heap, which is used for dynamic allocation of memory. So in order to see how our recursive function we just defined here affects these two data structures, let's just go through it step by step. By looking at the example. So basically what we want to do here is we have a list containing 2 elements, 1 and 2, and we want to sum up this list with our just newly created recursive function. Okay, so when you start the execution, the call stack of the program usually only always only contains the stack frame for the main stack, right? That's basically how your function execution starts. You can basically imagine your call stack as the thing that gets printed whenever you have an exception, right? When you have an exception and you print it to the console, it always shows you what was called until the exception was triggered. And that's basically what the call stack is, and that's basically where the exception takes this information from. So the first element on the call stack is always the main function, the main script you're executing. And as soon as you enter a new function or a new code block, a new stack frame is pushed onto the stack, right? So let's see what happens here. First thing we have to do in order to execute our script is we first have to create the list in the heap, right? With our 2 elements. Since it's a linked list, we have 2 objects here. The first one contains the element 1 and a pointer to the second list object, which contains the element 2 and the empty list as the tail. Okay, now we can actually execute our sum function, and what happens now, since we are executing a function and we go into a new scope, a new stack frame is pushed onto this call stack. And in this stack frame, there are actually more information than just what the function is. It also actually contains the arguments of the function, which in our case is a pointer to the list we gave to it, right? So we call this function here, and we provide the list we just created with the 2 elements. Okay, let's jump into our function. our function now checks which constructor the list is actually using. And in our case, our list is not empty, right? Because we are starting with the first node, which contains the element 1. So we jump into the second case. And the second case now tells us, okay, if you have a node, right? If you have a list which is not empty and it has an element, what you have to do is you have to take the element and sum it up with the add it up with the sum of the tail of the list. Okay. Since the result of sum of tail, right, the sum of the tail is not known yet, we have to execute the sum. We have to compute the sum of the tail first. So we call sum again, which then leads to sum getting put onto the call stack as a new stack frame. And now the argument of the sum function is actually a pointer to the tail of the list, which is, where's my mouse? Which is this part here. Okay, so just as before, we go through the sum function again. We notice that the list is not empty. It actually contains the element. Since it contains the element, we just do our addition again. And in order to do the addition, we have to compute the sum of the tail again, which is the empty list. So we call sum again, which creates another stack frame, another stack element with our last iteration. And as argument, it provides the value of the empty list, which is 0 in the compiled JavaScript code. So now we execute sum a third time, right? And now we actually are in the case where we have a value. Since the list is empty, right? We know that the sum of the list has to be 0. Okay, so we do not do any recursive calls anymore. That's nice. So we now actually we know the return value of the second sum call we did. So what happens now is that this function returns here, and every time a function returns or we exit some scope, the stack frame, the last stack frame, is removed from the stack, and we continue with the stack frame that was called before. So the sum function with the empty list returns, and we go back to our second iteration of the sum, and now we can compute actually the second value, so the sum of 2 plus 0. Since we now know, where's my mouse? We now know what this sum is all about. So since this function now also returns, we can remove another stack frame from the heap, compute the first iteration of sum 1 plus 2 now, and in the end we arrive at our solution 3, and our call stack is empty again. Okay, so one thing you might have noticed is when we did this recursion, that every time we traverse to the list, right, for every element within the list, we added another stack frame to the stack, which worked fine in our example since there was enough space on the stack frame and we didn't have actually that many elements. But you might imagine, since this call stack is usually very limited in space and the number of elements it can contain, that as soon as the list grows very large, there might be some problems with it. And in fact, we can try that out. And execute the sum operation on some larger list. In order to do that, I will quickly write some generate function, which can generate a huge amount of elements for a list. What I'm basically doing is we have a parameter n, which contains the number of elements we want to generate, and as long as n is greater than 0, we generate one new element and then recursively call generate again and reduce n by 1. So we just add another element. It doesn't really matter in our case, for our example, what the element is. Let's just do it all, let's just take the element, all elements are 1, right? So that we now by the n we provide what the sum actually is supposed to be in the end. And if the n is 0 or smaller than 0, we basically just want to return the list we generated. Okay, this is a small generator. So let's create some variable list, which has maybe 10,000 elements. Okay, and let's call sum on it, and let's print the result, right? And everything works fine. This should just print 10,000, right? let's do that and execute the code. Range error, maximum core stack size exceeded. Okay, so what happened here? Maybe you already know or can imagine, or maybe I already hinted at it a little bit, but the call stack size was too small to fit all of our recursive function calls, right? Since every time we traverse through the list and look at the new element, we create a new stack frame. And it's actually a quite well-known error in computer science. I don't know if you know it, but there is the site called Stack Overflow, which basically was inspired by this error. And in this animation I just showed, you can see what actually happens when we encounter the Stack Overflow, right? We fill up the stack with stack frame, stack frame, stack frame. We go through it recursively, and at some point there's just no space left, and the stack blows up and flows over. Okay, that's not very good, right? You might be thinking, okay, if we have this problem with recursion, why should we even use it, right? Why can't we just use our usual while loop or for loop and just stick with our normal imperative programming or object-oriented programming? What does functional programming even give us when, this pattern actually limits us in the size of a list we can traverse? And you're absolutely right, right? This is a huge disadvantage of a recursion, but there's actually something we can do. Because there's a special type of recursion, a special kind of recursion, which can be optimized by most functional language compilers to use, in the best case, constant stack size. And this kind of recursion is called tail recursion. And the idea behind this is pretty simple. The only thing that differs between recursion and tail recursion is that within tail recursion, the recursive call of the recursive function happens as the last statement in the function body. Sounds pretty simple, but in most of the cases, you actually have to do some thinking or rearranging the problem in order to get there. So let's look at our sum function and check whether it's already tail recursive. Okay. Let's look at sum, right? In the only recursive call we have is in the case where the list contains an element. And we can already see, right, before we can actually compute the sum here, we have to compute the sum of the tail, which means that after we have computed the sum of a tail within the recursive call, we actually have to do another execution before the function can return. This means that in our current definition of sum, we are actually not tail recursive because the tail call, the recursive call, is not the last statement which is executed within that function. Okay, so let's think about how we can change that. So what we have to do is, right, get rid of this addition operation here. Okay, let's think about how this addition actually works, right? As we have seen in the slides before, what basically happens when we execute this is we build up this chain of additions, right? We first look at the element 1, then we compute the sum of the tail, which is basically just this, right? We have our brackets, right? Our precedence. We first have to compute the sum of the tail before we can compute the rest of the sum, right? We basically have to stack up all these things. We basically have to look at the last element before we can compute the first element, before we can get rid of the first element. Which is not what we want, right? That's basically what prevents tail recursion. So what if we can now switch the precedence, right? What if we can say, okay, but I actually want to compute 1 plus 2 first before I actually compute the tail. At the sum of the tail, right? Compute this first, then we have only one thing left, and we can then happily compute the sum of the tail. And what we can do in order to do that is to add some intermediate state variable again, and define our function sumTailRec, which now gets a list and some intermediate state. And this intermediate state is now the intermediate sum of all the operations. So basically what we are trying to achieve now, we are going through the list And every time we encounter an element, we add this element to this intermediate sum, and then we provide this intermediate sum to the recursive call, so that the recursive call in the end is the last statement within that loop, within that recursion. Okay, let's see how that looks in code. Right? If the list is empty, we know that there is no element left, so what we can do is we can just return out our intermediate sum, because then we know that our intermediate sum contains all the additions of all the elements. If our list is not empty and we actually have an element, what we have to do is we first have to add the element to our intermediate sum, and then we can call the tail, the recursive call, and provide the tail as the new thing to look at, and the new intermediate sum as the second argument. Okay, this seems to compile, right? And we can also see now that the last statement which is executed within that function is now our recursive call, right? And if we actually look at the generated JS code, we can see that the two definitions of our sum function are actually quite different, right? If we look at this JavaScript function which was generated from the recursive function definition, we can see that it actually uses recursion, right? It actually calls sum again. But if we look at our tail recursive definition of sum, we can actually see that it uses a while loop, right? It doesn't even call sum tail rec in the body. And that's what happens when the compiler of ReasonML optimizes some tail recursive function. It actually transforms it into a while loop, which is constant in stack size, right? And when you go through a while loop, you don't create the stack frames as you would when you do a recursion. Okay, so but before we continue, let's maybe first execute the function to see whether our tail recursive definition is actually able to handle the huge amount of list elements we have here. Okay. Right, so, oh, oops, yeah, that's list, of course. Okay, so basically what I'm doing here, I'm calling some tail rec, and the intermediate result is 0 in the beginning, right? Because we want to add up the things in the end, and it doesn't actually make any sense to provide some other value, because our sum should be 0 in the beginning, since we haven't looked at any element yet. And I provide the list that was generated with 10,000 entries. And let's execute the code and see what happens. First clear the terminal. Boom. Okay. Our tail recursive definition of sum was able to compute the sum of a list with 10,000 elements. Okay. Let's do this with our other definition again to see that it doesn't work. And execute the function. And all right. The tail recursive function printed 10,000, and as we got to the sum, to the recursive function, it threw a stack error again, stack overflow error. Okay, that's pretty neat, right? Yeah, so tail recursive is a good way, or is basically the preferred way you should deal with recursion in order to have the same benefits as you would have in your imperative programming language with a while loop or for loop. But with the tail recursive definition of a function is actually, in some cases, not that simple, right? In most, or in some of the cases, you actually have to rephrase your problem in order to be able to define your function tail recursively. There are a few things you can try out first, right? There are a few tips you can do. For example, it's always a good idea to maybe try to identify some intermediate result, as we just did with our sum function, that you can provide as an argument to loop through. But this won't help in some of the cases, right? There are more complex cases where this might not give you any benefit. One other thing which you might be interested in when you I don't know, want to learn more about how you can transform recursive function into tail recursive function, is some pattern called continuation passing style. It's basically a Kickstarter for transforming simple recursive function into tail recursive functions. I won't go into it in this talk, but if you have questions about it in the Q&A afterwards, you can of course just ask me and I can go into more detail about it. But what it does is it can basically help you to identify what kind of intermediate states you want to provide or how you can rephrase your problem when transforming recursive functions into tail recursive functions. And with that, we are actually at the end of our talk.
Yes. Right, so that concludes what we have prepared. Maybe once again to wrap up, what was the focus of that talk? What we wanted to show you is what are the challenges, what are the experience you probably make when you switch from an imperative language like Java to a functional programming language like Reason. We did this with the Reason language because we believe it's a very strong and useful language. We made good experiences with that language in our own product, and we hope you could, with this talk, do like two things. First, introduce you a bit to the Reason language, but also show you what are the challenges when you switch from imperative programming to functional programming language as a programmer and how to overcome them. Yeah, we are still here up for any Q&A session you want to make. We can discuss what Arne mentioned, of course, about this pattern style for transforming to tail recursive functions, but we can also talk about a bit more about the experiences I made switching from being a Java developer to being a Reason developer, or the experiences we made in our team using this entire ecosystem. Just let us know what you are interested in.